This is Matteo Riondato. He's a professor at Amherst College. He graduated with a PhD from Brown, and he still has a lot of connections to this university, so we're happy to have him back. He has an NSF Career Award, and other than that, I'm sure he has many accomplishments, but I don't remember what they are. But I can definitely tell you that he is a great advisor and teacher and researcher, and I'm excited to hear this talk about data mining and Markov chains and sampling. So with that, I will pass it over to Matteo.
All right, thank you, Mariam. Thank you all for being here. I'm so happy to be back at Brown. Things really have changed for Theory Lunch, definitely. I mean, first of all, it's not only called Theory Lunch anymore, I guess. But in March 2009, Fabio Van Dien, who used to be a postdoc here, and I actually cooked Theory Lunch in the third floor kitchen for about 20 people. So we made a meal for 20 people, and then I think someone else gave the talk, but we literally cooked from start to finish everything on the third floor. I think we made some kind of pasta, but it was very different. So anyway, yeah. So things change, yes. But again, it was 17 years ago, so things, yeah, time flies. Yeah, so this work was Michelle's honors thesis. She was an undergrad at Amherst. Amherst is an undergrad-only institution, which we then transform into a paper that was accepted at and you know, for the PhD students there that are looking for faculty jobs, I would suggest to not underestimate a career in a small liberal arts college, especially in a good place like Amherst that produces graduates like Mariam and Alex, both of whom work with me at Amherst. And so, you know, don't only look at R1s. You can do amazing work with undergraduates. Cool. And yeah, so we're going to talk about this weird way of performing some operation on binary matrices, basically, for something called fast null modeling, and I'm going to tell you about what it is. And the new algorithm that we propose, it's interesting because it performed this operation called curveball trades in a streaming fashion, basically doing two passes over the data. But just to frame a little wider what my research is about, if you open a data mining or data analysis, data science book, you usually see a picture like this about how extracting knowledge from data works. So basically, you know, you have your data set, you do some processing, you need some deeper querying of this data set, and then you get your output for the analyst. Actually, I think this slide was made by Alex originally, maybe, years ago. So what I'm doing in my research is kind of expand this model to be a little bit more statistically sound. And that's actually the title of my career award, Statistically Sound Knowledge Discovery from Data. And the idea is that the data that we get, it's not, you know, the whole picture, right? It's just a partial representation and a random and noisy representation of some data generating process, okay? And in the end, the goal is not to extract information from the data set, but is to better understand, to gain new knowledge about this unknown, partially unknown data generation process. And what we observe, this observed data set, you know, again, it's a very partial representation of the DGP. And what we know about the data generation process can be modeled as something called a null model, which basically is a mathematical representation and formulation of everything that we know or assume about this data generation process. And so by using, you know, both the observed data and this null model that we formulate, we perform our data analytics steps, but at the end, we also have to perform a statistical assessment, basically a testing of whether the information that we got from our data set really is new information about the data generation process, or is just due to the randomness in the observed data set, basically. Okay. And then the great thing is that basically if with the results that we obtain from the data sets pass this statistical assessment and become part of the output, then there is a feedback loop to enrich the null model for following steps, right? Because now we have new knowledge about this data set that becomes, about the data generation process, that it becomes existing knowledge and so on. And so, this is a much more, if you're a statistician, this is what it is. I mean, that's how we have been doing statistics forever, right? And that's kind of partially true. What I'm really interested in are the computational challenges that exist in this step, basically. Okay, so statisticians have given us a lot of methods to test hypotheses and perform all kind of perform this assessment in all kind of ways, but they rarely put the attention into how scalable their methods are, right? In terms of both the size of the data, but also the number of questions that we are asking about the data, so the number of hypotheses that we are testing and things like that. Okay. Also, feel free to stop me if you have any question about anything. Okay, so that's the general picture. So let's try to give a bit more, a more concrete example. Okay, so we have a set of researchers, okay, and some papers, okay, and we can observe, which papers were co-authored by which researchers, right? And so we can put a 1, okay, where this researcher authored this paper, okay, and so this author, and so this author, okay. So this is just a 0-1 matrix, like a binary matrix, and it's basically the incidence matrix of a bipartite graph, right? You can put papers on one side and authors on the other side, and when there is a 1, you connect them with an edge, okay? But I'm actually only going to talk about this binary representation, and really what I'm going to say can be used for any kind of sets or collection of binary vectors. Okay, and so that's why in the title we talk about hypergraphs, graphs, binary matrices, anything that you can really represent with binary vectors. Okay. So this is what you observe, right? And you want to analyze it, and then you claim that, for example, the likelihood that two women co-authors a paper is some percentage based on some analysis that you perform on the data set, right? So how do you actually know whether this result is statistically sound, whether it's really, giving you information about the process that generated the data, okay, the process of co-authorship, right? And so the issue here is why, even positive question. Well, because if we collected the data at a different time, for example, we may have observed a different data set, right? Not only just more papers or different papers, but different set of authors and things like that, right? But yes, it's going to be a different data set, but this is going to be really a completely arbitrary binary matrix. Well, for example, we can think, well, I'm not going to observe a matrix of all zeros, right? Because, papers are authored by someone. So definitely every entry has at least one. And so every row has at least one. And, I'm going to include someone in the, some researcher only if they author at least one paper, right? So again, it's not that I can observe a matrix of all zeros, but also not everybody authors every paper, so I'm not going to observe the matrix of all ones. So I need to set some constraints on what data sets I may have observed. And a very common set of constraints that is introduced is by fixing, okay, assuming that the alternative words, the alternative data set that they may have observed are all the matrices that have the same row sums and the same column sums as the one that I actually observed. Okay? And the idea here is that, for example, I'm preserving some important properties. For example, the column sums kind of may preserve like the productivity of an author, right? Or how long they have been active, right? Persons with a longer career usually have more papers, right? And by preserving the row sum in this example, right, I'm preserving the fact that there are not, papers, not a lot of papers with 200 authors, right? But there is a distribution of possible number of authors in some sense, and that's what I'm preserving, okay? But everything else is free, okay? So I can observe any matrices with the same, I may have observed any matrices with the same row sums and column sums as the data set that I actually observed, okay? And there are a lot of them. Like just to be clear, it's even hard to count how many there are, okay? And they may look very different from the one that we start with, okay? The one that we observe, okay? But they all have the same row sums and same column sums. And now if you squint, yes, good. Sorry.
Quick question. Does the order matter? The row, column order?
Great questions. You should ask Alex and Mario because they wrote a paper on this. But we're gonna assume that it's fixed, but you don't have to. Okay, so everything we are gonna talk about also holds where instead of having like a sequence of binary vectors, basically, you have a set of binary vectors, so where the order doesn't matter. Okay, good, great question, sir. And yes. There are something that you need to fix, but all you're doing is changing what is your set of possible words, right? Good. Okay. So now, if you squint enough, you will see that what I highlighted here, and by connecting also with the rows, with the arrows, is in what entries, okay, that matrix differs from the previous one. Okay, so for example, this one differs from this one in these entries. Okay, this one differs from this one in these 4 entries. Okay, and stuff like that. All right. And this is where if you have taken 155, you start knowing, oh, this looks like a Markov chain where I start from some initial point and then perform some perturbation and I'm moving across this space. Okay. And indeed, that's the case, but let's focus a little bit how we are actually using these matrices. And again, I'm still introducing the problem. We're not talking about our algorithm yet, but I'm motivating why I'm interested in these alternative words, okay? So the idea, again, is that we have some result that we obtain from the data set, and we fix some null model, basically, which is, for example, all data sets with the same row sums and column sums as the one they observed. And I have a probability distribution over this set of data set, collection of data sets. And for the purpose of this talk, let's assume that this is the uniform distribution. Okay. To perform that statistical assessment that I was talking about, I have to formulate a null hypothesis, okay, that involves the result that I observe and the null model. And for example, it could be that my observed result is equal to the expectation, okay, according to the probability of over all the possible words, okay. And then I can do my classic statistical test that some statistician gave me, okay, and compute my p-value. If I'm testing multiple hypotheses, I will correct for them and stuff like that, right? What's the issue? Well, here is where we got into the computational issue, is that usually to compute those, you cannot really compute those p-value explicitly. There is no formula for that, okay? So what we're going to do is approximate that p-value by sampling from the null model, okay? So artificially generate alternative words, basically, okay, in a Monte Carlo fashion, and compute an empirical p-value, okay? And so the key computational step is to actually generate potentially millions of matrices from my null model, okay? And remember that I only have access to the observed data set, and this is where the Markov chain Monte Carlo approach will come into play, okay? How familiar are people with Markov chains? First of all, let's be good. Okay. So basically, what other people have developed is a Markov chain over all the matrices with fixed row and column sums. Okay, this is someone else did that. They proved that it's strongly connected. The space is strongly connected. Okay, so I can move from any matrix to any other matrix with these properties. If I move in the right way, I can get the uniform stationary distribution. The issue is that it's very hard to prove bounds to the mixing time, and they're only known for extremely special cases. Basically, if all the rows have the same sum, basically, okay? Or if you think about that in terms of graphs, if the graph is regular, okay? So everything has the same degree. Okay, and so the key question is, okay, how do you move, right? Given that you are in one state of the Markov chain, how do you select the neighbor of that state on which you are going to move to, right? You sample a neighbor according to some probability distribution. And the idea is that, well, you're going to take two columns, for example, in this case, two authors, okay, uniformly at random, okay? And then you're going to swap some of their entries, okay? So by swapping, I mean, for example, that in this row we had 1, 0, and in the next state it's going to become a 0, 1. And down here, I have a 0, 1 that becomes a 1, 0. Okay? And notice that this maintains the row sums and the column sums. Okay? And it doesn't have to be limited to these, to swap 4 entries at a time. Okay? I can swap more than 4 entries. Okay? But let me now get into the details of how do I select which papers or which entries to swap. Okay? So again, this is an existing framework, which was, it's called the Curveball trade. There is a whole baseball trading card metaphor here going on in the paper that presented this, which also did not present it in the way that I'm presenting it to you, which is kind of one of our contribution to present this Curveball trade as a sampling process. All right. So again, it's going to be a sampling scheme. So I have to define a population and a sampling size, and then tell you what I'm going to do with a sample of that size from the population. Okay. So my population, given the two vectors, are going to be the indices that have value 1, essentially, in the exclusive OR of my vector. Okay. So these are the papers that are authored exactly, for example, by one of U and V. Okay, I thought I highlighted them, but for example, this would be row 1, row 2, row 3, row 4, not row 5, because it's 1, 1, yes, row 6, and not the last one. Okay? My sample size is going to be the number of papers that are authored by U, but not by V. So these are the rows where the number of rows where I have a 1, 0. Okay, so for example, this row, and I think that's it. Okay, so in my case, the sample size will be 2. Okay, and so I'm gonna draw K papers uniformly at random from P. Okay, notice that I'm giving you the way that a statistician, I'm presenting this to you the way that a statistician would. I'm not telling you how to do any of these operations. Okay, I'm telling you what are the mathematical objects that I'm working with, and kind of what to do with them, but not how. And obviously, what I tell my students is usually that's what makes us computer scientists. We care about how things are actually done, and not just what things we're actually playing with. Cool. So we draw this uniform sample of K papers, okay, without replacement, uniformly random from our population. And basically, we're going to use that to update our vectors and create two new vectors. Okay, papers that we that belong to the sample. Okay, becomes a paper that is co-authored by U but not by V. So for example, we will have a 1 in the U vector and a 0 in the V vector. And vice versa, anything that was not sample is going to be a paper co-authored by V but not by U. Okay, so we'll have a 0, 1. So I think I have an example. Yeah. Okay. So for example, as we were mentioning, right, this is our population. Okay. And our sample size is 2. Okay, these are A and C. Sorry, why is it on C? Okay, sorry, yeah. There are 2 more lines, yes. A and C, okay, these are the papers that are co-authored by U but not by V. Okay, I take a sample, okay, of size 2 from my population. So for example, I have C and D, which I saw marked in blue here, and the other elements of the population are not are in P minus S, okay, in the remainder, and I can use this, okay, to obtain the transformed vectors. Okay, I set to anything that is not in the sample, I set 0 in U and 1 in V, and vice versa. Things that are in the rows that are in the sample, I set them to have 1 in U and 0 in V. Okay, and so this ensures to maintain the same rows and column sums as the others. And again, I haven't told you anything about how I'm going to do that. But just know, again, someone else already presented the curveball trade and said, okay, this forms a Markov chain, blah, blah, blah. We can prove the Muxin time in some cases, and whatnot. But they didn't really go into the details of how to do this. Cool. We good for now? Okay. So let's talk about how to actually do that. And this is an existing algorithm called fastball. Again, baseball metaphors here. And so the idea is that you're going to compute by iterating through the rows. Okay, so you're going to go through the rows and compute these 2 quantities. Ku, which is the numbers authored by U but not by V, which is exactly equal to our parameter, our value K that we are interested in. And Kv, which is the number of papers authored by V but not by U. Okay? And then we're going to create some auxiliary vectors that will contain letters, basically. Okay? We contain KUUs and KVVs. Okay? And notice that the number of entries in this vector is exactly the size of the population. Okay? We're going to shuffle this vector, okay, randomly. Okay, and then we're going to iterate again through the rows, okay? And when we encounter the ith element of the population, we're going to use the corresponding element in the auxiliary vector to update the vector, okay? So for example, I start, okay, this is an element of the population. In my shuffle vector is a V, so basically that means that I should have a 1 in V and a 0 in U, okay? And I can keep going. B is also an element of the population, so I use the second one that I saw. I use the second element of my auxiliary vector. C, it has a U, so I set it to 1 in U and 0 in V, and so on. Okay, and then at the end, what I get is again something that has the same row and column sums as the original. Okay, so this is again an existing algorithm. And if you look at it, it basically costs like 4 passes over the data, okay? Because I need to compute Ku and Kv, and this requires me to iterate over all the rows, okay? I need to create and populate my auxiliary vector, which may be as large as the number of rows, okay? Then I need to shuffle it, which if you use like Fisher-Yates, again, is a linear time algorithm, so it takes again linear time, and then I need to go explicitly over the vectors again to set the entries according to what the auxiliary vectors tells. Okay, so that was interesting, and in the sense also that it didn't have that fashion of like sampling from the population that I was giving you before, right? But so we actually had to understand how they were actually doing that. once we understood that that was what was needed. But what we also noticed that 4 passes seemed too much for us. And so what we really wanted to do was seeing if we could develop a faster algorithms for performing these trades. And why is that interesting? Well, because the total cost of running a Markov chain, often as theoreticians we think, oh, it's just the mixing time, right? Oh, by the way, it's very funny because I don't think of myself as a theoretician, but okay. That's, when Ellie admitted me for the PhD program, I told him that I didn't want to do theory. But anyway, and I guess he was kind enough to let me do not theory, I guess, but we're still proving stuff. Okay, anyway, so the mixing time, right? But the mixing time only tells us part of the story, right? You can always design a Markov chain that has a mixing time of 1. You just have to connect every state with everything else. The problem is that you don't know how to move, right? That's the whole problem in designing the Markov chain. So really, the time that a Markov chain takes to mix before you can actually draw a sample is the number of steps times the time that it takes to make a step. Okay? So what we are doing here is acting on this second factor. We are trying to reduce the time that it takes to select the next state of the Markov chain. Okay? Bring it down from 4 passes to 2 passes of the data. Okay, basically. And you might say, that's not a lot, but in practice, wouldn't you be happy if you were paid twice as much as you're paid now? I would. So a 2 times improvement is still significant in this kind of cases. Also, you cannot do it in less than 2 passes. So basically, what we have is the optimal algorithm for this. I don't have explicit proof for this, but basically, before you look at the data, you know absolutely nothing, and you cannot actually build all the information that you have in a single pass. So you need at least 2 passes. Okay, cool. And in order to develop this algorithm, we're going to use my favorite algorithm of all times, which is reservoir sampling. Okay, reservoir sampling is a very well-known technique. It was developed by Witter, who at the time was still a professor here, I believe, or close to it, or he just left maybe, and Jeffrey Witter. And the idea is that you have a stream of elements, okay, which could be of any length, okay, including a length that you don't know in advance, okay, and it could be basically infinite, okay. And you want to sample some known quantity, okay, from the stream, of elements from the stream, okay. And the way it works is that you are going to put the first 2 papers, or the first K papers, in a reservoir, okay, of size K. So I look at the first paper, okay, I put in the reservoir. I see the second paper, I put it in the reservoir. At this point, the reservoir is full, okay. The third paper arrives. I'm going to flip a coin, okay, that has success probability, the size of my reservoir over the number of papers seen so far. Okay, so in this case, this is the third paper I see. My reservoir is size 2, so my success probability is 2 over 3. Okay, and let's say that in this case, my coin flip does not succeed. Okay, so I'm not gonna do anything with C, and C is not gonna be sampled for sure. Okay, I see D. I flip a coin, which now has a different bias. Okay, 2 over 4 because I saw 1 additional paper. If and assume that I now have a success, okay? Now that means that I want to put D in the reservoir. But the problem is that the reservoir is already full. So what I'm gonna do, I'm gonna select one of the elements in the reservoir uniformly at random and replace that with D, okay? So in this case, there was A, I select A at random and I replace it with B, and so my reservoir now contains D and B. And then I see E, I flip my coin, again with a different bias. In this case, it doesn't succeed, and so on. Okay? The great thing about reservoir sampling is that at every step, what you have in the reservoir is a uniform random sample of the elements that you have seen so far. Okay, so it's not just true that if your stream is finite, at the end of the stream you have a uniform random sample, but at every step, okay, at every time step, what's in the reservoir is a uniform random sample of what you have seen so far. Okay, and it just requires flipping a coin. That's why I think it's so cool. And there's basically no additional variables apart from keeping track of time and having the space for the reservoir, which you need because it's basically the space that you need for your output. So it's very elegant, very simple. Okay, so we're going to use this technique. Okay, so when someone tells me, okay, so I selected vector u and vector v, okay, I haven't looked at u and v yet, okay? So I actually don't know what the size of my population is. And that's great because the population is going to be, what I want to run reservoir sampling is. And reservoir sampling is exactly done for cases where I don't know the size of my stream. So that's good, right? It seems like I could potentially use reservoir sampling because I don't care to not know how many elements there are on my stream. The problem is that we also don't know our sample size, okay? If you recall the slide that I had before, I said, I want to sample k elements from my stream. Well, but now I don't know how many they are because, again, the sample size depends on my vector, and I haven't looked at my vectors yet. Okay? And so the idea is relatively simple. We're going to assume that our sample size is large. Okay? So we're going to sample more. But as we see elements in the vector, okay, we're going to shrink the reservoir. So we're going to sample fewer elements. Okay? As we progressively figure out how many we really have to sample. Okay? So more formally, what we're looking for is an upper bound to my sample size k, such that R0, so my initial sample size, I can compute it before really looking at the contents of my vector. Okay? And then I have a sequence of upper bounds that basically decrease in time. Okay, decrease over time, and such that the last one, once I have observed all the rows, okay, this is exactly the sample size I was interested in. Okay, so in that sense, it's tight once I've done one pass over my data. Okay, and I can compute it basically in a streaming way. Okay, so the value of my upper bound at time I, okay, is a function of its value at time I-1 plus n of the elements that I'm currently looking at. Okay, so it's a function of the previous value plus the elements of the vectors that I'm actually looking at. Okay. Okay. So let's see how we can derive such an upper bound. So if I only know, so right now I'm interested in finding out what is our initial value for the upper bound R0. One may say, well, if I only know that I selected these two co-authors, I have nothing to base that on. Okay, maybe the number of rows, right? But that seems, excessively large. But really, if you think about what your input really is, you can think that the rows, the column sums, are also part of the input because they don't change, right? They are maintained fixed throughout the process. Okay, so you can think that either they come with the input, or you can, do a fast preprocessing at the beginning and then consider them fixed or something like that, right? And remember, you have to take a lot of samples, so this cost gets amortized very quickly if you need to. So I can take the number of papers authored by you in this case, okay, so the column sums of you, as my initial upper bound, okay, and this is larger or equal than k, because remember, my k is the papers authored by you, but not by v. And in this sum, I have both papers authored by you and not by v, but also papers that both of them authors. Okay? So my initial bound, for example, in this case is going to be 4 because that's the column sum of 4. And then I start looking, okay, at my vector, and I want to refine this upper bound. So for example, okay, so I look at the first row, and I have 1, 0. And this doesn't really give me any additional information because basically that for all I know, there are 4 rows that have 1, 0 here. Okay, so I cannot really refine. And so my bound stays the same. 0, 1, similarly, doesn't give me much information because, again, for all I know, there may still be 3 left, three rows left that have 1 and 0. Okay, and so I keep going, and as long as I see 1, 0 or 0, 1, my bound, my upper bound doesn't really change. But once I see a 1, 1, okay, this is a paper that was counted in my upper bound, but doesn't actually contribute to K, okay, because this is a paper that is co-authored by both, and so it's not included in the count when I count papers co-authored by U but not by V. So in this case, I can shrink my upper bound to my sample size, okay? So basically, what my bound becomes is R0 minus the number of papers authored by both U and V up to row I included. So basically, the column sums of U minus the number of papers where I have a 1, 1, minus the numbers of row where I have a 1, 1. Okay, and I can I can compute it basically in streaming, right, by defining this function, which is 1 if U and V are both at 1 and 0 otherwise. Okay, and so I can continue using this operation, and once I observe the last row in this case, I get 2 as my sample size, which is exactly the quantity that I was interested in. Okay, so what we have here is one possible upper bound that can be, again, can be initialized very quickly, okay, using information that I have. It can be updated very quickly and converges to the actual size that I'm interested in. All right. So how do we use that? So this is our algorithm. So basically, we start with an empty reservoir of size the number of column, the column sums of the vector U. Okay, and what we're going to do then is basically run in parallel reservoir sampling and this refinement of the upper bound. Okay, and when the upper bound gets refined by decreasing by 1, when we see a row of ones basically, then we will shrink my reservoir by removing a random element from it. Okay, so we start by, we initialize the reservoir, it's empty, and then we go through the rows, and if I see an element that, if I see a row that has, both entries at 1, if my reservoir has empty slot, I just shrink it by removing one of the empty slots. Otherwise, which means that the reservoir is full, I take an element from it and just evict it from the reservoir, and then I shrink the reservoir by removing the slot that is now empty. Okay? And instead, if I have an element of the population, so I have an entry that is 1, 0 or 0, 1, I'm going to update the reservoir just using reservoir sampling. Okay? And so this constitutes, this for loop basically performs the first pass over my rows. Okay? And so at the end of the first pass, right, what I have in the reservoir is a uniform random sample of my population, which is exactly what I wanted to create. And so in the second pass, in this second for loop, all I'm doing is using this sample to update the entries using the same update formula that I had before, okay, for the curveball traits. Okay, so if the elements if the index is in the reservoir, then I set UI to 1 and VI to 0. Otherwise, if it's an element of the population, I set it to 0 and to 1. Okay, so the key component is obviously this this first passes over the data that performs in parallel both the sample maintenance using reservoir sampling and the selection of the correct size of the sample by shrinking the reservoir when I update my upper bound, basically. All right, so let me give you an example. So at the beginning, again, we have our upper bound to 4, okay, and our reservoir that can contain 4 elements, okay. The upper bound is still 4 when I see the first row, okay. R as an empty slot, so I continue with, I do reservoir sampling here, and I add A to my reservoir. When I get to B, my upper bound is still 4, it still has empty slots, so I add B to my reservoir. Same for C, okay, I add C to my reservoir, and I add D to my reservoir, okay. Now, when I see E, okay, my upper bound has shrunk now, so, and the reservoir is full, right, because it has size 4, so I need to select one of the elements in the reservoir uniformly at random, okay, for example, A, and I'm going to shrink the reservoir by 1. So basically what I'm doing, I'm now shrinking the reservoir, which now contains only B, C, and D, and it's still full, okay, because it only can contain 3 elements now, okay? And I continue, okay, F, I see F, my upper bound doesn't change, okay? I perform reservoir sampling, okay? I flip a coin with that probability 3/5 because 3 is the size of my reservoir and 5 is the number of population elements that I've seen. I get head, okay, heads. So I perform reservoir sampling. I evict an element from the reservoir uniformly at random and I replace it with F. So now I have BFD in my reservoir, okay? I go on to the next row. I shrink my my upper bound, so that means I need to shrink my my reservoir, okay? So I choose an element from it uniformly at random, I evict it, and I shrink the reservoir by 1. So now it has size 2, which is exactly the size that I need, right? So I converge to size 2, which is the size that I wanted my sample to have, and I also have the sample at the same time. Okay, and in the second pass, right, I'm just using my sample to set the entries to their correct values. Okay, if it's in the sample, it's going to be set to 1, 0. If it's not in the sample but it's in the population, it's going to be set to 0, 1. And those that are 1, 1s or 0, 0, they remain the same. Okay. And so the correctness is really relatively basic. What we really have to show is that after the first loop, okay, after this loop where I compute the reservoir size and the sample at the same time, what I have in the content of the reservoir is a uniform random sample of size k. And we know, well, we saw from the properties of the upper bound that at the end it really converges to the correct size, so that's good. And then the idea is that, well, we are either, at every iteration, we're basically either doing nothing if we have a 0, 0, or we are doing reservoir sampling or resizing the reservoir. When we are doing reservoir sampling, well, we can rely on the properties of reservoir sampling, the fact that the content of the reservoir are a uniform random sample of the elements seen so far. And when we are shrinking the reservoir, because we are choosing an element uniformly at random from the elements that are in it, we can use the fact that the uniform random sample of a uniform random sample is a uniform random sample. Okay? If you start from a larger sample that is uniform, you select random elements to remove from it, what you get is still a uniform random sample of the original population, just a smaller one. Okay? So there's kind of these transitive properties of sampling, if you want, that you can perform it in stages, as long as you're doing it in the, if it's uniform, just if you're doing it uniformly. Okay, so that's really the basic idea behind the correctness of the algorithm. I'm gonna kind of go faster here, but the idea is that you can have a different upper bound where instead of using the column sums of U, you're basically using the number of rows minus the column sums of V. Okay, basically this gives you similar information, and there is a similar update rule. Notice that in this case, for example, we have 7 rows, and the number and the column size of the column sums of V will be 5. So my initial upper bound will already be 2. So basically, I would actually get exactly the correct value immediately. So there is not even shrinking ever happening. I have, with one from the beginning, I have a sample of the correct size. And so the algorithm implemented basically always takes the minimum between these 2 upper bounds to get the best upper bound to the sample size. That's just a refinement. Okay. I guess we are not repetition because we also implement our algorithms, and we take very good care that they are as fast as possible, and also that the competition is as fast as possible. My students have become very good at using advanced features of Java and other things to insert a lot of optimizations for all the algorithms that we implement from scratch. So what we're going to see here for different real case data sets that are sorted in increasing size, we're going to show the time that it takes to perform a trade, okay, a Curveball trade, so one of these operations, for both Fastball, the existing algorithms, and our new algorithms. And on the left, you're going to see absolute times, and on the right, you're going to see normalized times, where essentially we normalize by the time for Fastball. So all the average time for Fastball are going to be at 1, and so we want to be below 1, okay, to show that we are faster because it takes less time. And basically what you see is that, well, we kind of deliver on our promise. We, instead of taking, we are basically 2 times faster, okay? And that's really because we move from 4 passes over the data to 2 passes, basically, in terms of how much the algorithm is doing, okay? So this actually led to the great thing about this is basically in the same time you can collect more sample from your Markov chain, and so get more accurate estimation of your p-values and perform statistical tests that you can trust more, because basically you have less uncertainty about where that empirical p-value really falls. So the message here is that there are important statistical steps that one needs to do when validating data analysis results. A lot of these algorithms, a lot of the hypothesis testing that we want to do in practice, you cannot compute explicit p-values. So what you're going to do is MCMC, you're going to take a Monte Carlo resampling approach, and usually that means running a Markov chain, okay? And well, you need to take a lot of samples, like millions or billions of samples. So you need to have fast Markov chains. So what we're working here is not on designing better Markov chains, Markov chain in different mix in time, but we are acting on existing Markov chains, but speeding up the selection of the next state, which still leads to a speed up. Okay. And that's all I have. So if you have any questions, I'm happy to take it. Thank you. Yes.
Hi, so I'm curious, what is the number of rows? What is the number of columns in this?
In many data sets?
Yeah.
So these are originally graphs. So sock opinions is around some hundreds of thousands, I would say, something like that. SX superuser is probably, I think this is one of your hypergraphs. Is that possible? Okay. Like in the million, I would say probably. Yeah. And it still doesn't take a lot of time. Yeah. Alex.
I have 2 clarification questions. So the first is this kind of like streaming coordination part of the contribution?
Yes, in the sense that the previous, Yeah, I mean, in the sense that we take the streaming, the cost as being how many passes you are doing over the data in some sense, or at least how many, convert the cost to like what's the corresponding cost if you had to do it in terms of the going over the data, if that makes sense.
Then I guess my second question is, because you're formulating this as a streaming problem, does this mean you no longer have to fit the entire data set in RAM?
That's also true.
Okay.
Yes.
So you can do this incrementally.
Yes. 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 And we also don't have like much extra memory, because in the end the reservoir gets small very fast, because real data sets are sparse. So there are, these column sums are very small, and so.
Very cool. Thank you.
I have a follow-up question, which is there a straightforward way to change fastball to be streaming in the same way, or?
Not really, because it relies on this additional vector that you have to create and shuffle. So, basically, if you want, what we are doing is taking the randomness that they need to shuffle the vector and use the same randomness, but throughout the stream, right, by performing this sampling, okay? And yeah, does that make sense? I presented you the most simple form of reservoir sampling. There are like more advanced ones that allow you to like skip elements, use less randomness and things like that are still possible to use in this case, but they are harder to implement, so potentially you can use less randomness even and more and get faster algorithms. Yeah, and I think in general also what we did is useful beyond our specific case. It's basically the idea that, I want to sample from a population of a known size, and the number of samples that I need to take depends on the population. So it's not something that I fix a priori, but it's a function of the data that I'm actually sampling, okay? And basically we're saying, well, if you can compute an upper bound and like refine it, then you can do the two things in the same time. So if you think of it as like just creating the sample, we have, an algorithm that kind of extends reservoir sampling to the case where you don't know how much the population size, but also you don't know how much you want to sample. Yes.
At some point, you made this comment about like 2 passes of a stream being necessary.
Yes. I don't have a solid foundation for that, but okay, let's talk about that.
Well, I guess my question is like, in what sense is that the case? And I mean, it seems to me like it very much depends on what the model of computation is. But if you allow yourself like random access to elements of the matrix,
then you can do it one.
Okay. Well, but then I guess maybe rather than measuring streams, you measure like how many entries of the matrix you touch. Yes, very good. Order of the number.
I think that's very cool. Yes.
And it seems like you should be able to do 1.5.
Yes, probably or maybe in expectation, something like that. Yes, I agree. Yes, so if you change this idea that you have to go in order, yes. Even so, let me tell you why I said 2. Because if you think of, let's see. So in the first pass, I create the sample, right? In the second pass, I use the sample to set the entries. I cannot set the entries while I create the sample, basically. So, yes, if you're not going to be in the sample, I can already know that you're going to have that value. So maybe I can set those ones. But those that are current in the reservoir, I don't know if they're going to survive or not, right? And those are past elements, so I cannot like jump back in my model of like streaming approach, right?
So I guess to me, what seems like it should get 1.5 is you do set things according to the reservoir, but when you need to remove something, when you take something from the reservoir, you go back and you switch it back.
Right.
And then either you don't have to switch that many things, or your reservoir guess was sort of the right answer from the get-go.
Yeah.
And then you shouldn't have to go back.
Right. Yes.
And I think it balances at 1.5 number of rows.
Probably true. Yes. I guess I don't know if it's exactly 1.5. It's probably ratio between the number of rows and the population size and your samples. Like it may be a function of that, right?
Okay.
Because
We should talk about it when we eat.
okay, sure.
It's also, I mean, if you have an access, something you can do it.
That's true. So if you have random access, it may be better to, and I'm not sure it's true, but let me tell you. You could compute the sample size and then do selection sampling or other things that simplify your operation a lot more. But we were thinking in streaming, and so we wanted to think it that way. Yes.
Yeah, sorry, I was just thinking about, because like, we haven't really used our knowledge of what the row zones are, and I was wondering if there's like...
Of the what?
Of the row zones, and I was wondering if there's like potentially an optimization there. If the row sum is the number of authors, then you know that like both of the authors did it, and you don't have to look at it, and if it was like one or less, then you know some things.
Great question. I don't have a good answer to this, but I can tell you that our we can prove that our upper bounds, of which kind of I told you a slightly simplified version, are actually optimal in the sense that at every point I can build the rest of the vector in such a way that the bound that I compute so far is actually the correct answer. So I'm not sure that there really is a way to use that.
Because I think in practice the number of columns is so large that, if it's like more than 2, it's like, it could be the 2 with the sample, or it could be literally anything else.
Yeah.
So it gives you not that much information.
Yeah.
Yeah, and it's probably never going to be like 1.
Right. Exactly. All right. Thank you all for coming, and thank you for the question.